Okay, on Friday we talked about conservation of mechanical energy. And we said the mechanical energy is conserved if there's no non-conservative forces doing work. So in this case, we said as it went down the hill, you had force of gravity and normal force. Gravity is a conservative force. It is doing work, but it's conservative, so we're fine with that. Normal force, not a conservative force, highly suspect. But as it goes down, it does, because it's acting perpendicular to the direction of motion, no work is done. So, is there any work being done by non-conservative forces? No. So mechanical energy is conserved. As we see this here, it can swap between your kinetic and potential, like your savings in your checking account. Total money in the bank still stays the same. But here we can see the total money in the bank stays the same. We can swap between checking and savings. But when we get down to here, you've got normal force, gravity, no work, but there's friction doing negative work. So it's negative work and causing the total mechanical energy to be lost. Okay, not conserved. Good with that? So today we're going to be doing, bringing in some math with this, but also some concepts. Okay. So, I'll give you some pennies. So on Nice. Rescued one. Okay, on a piece of paper, this is just a simple little tactile model here. Draw a little square that could fit a penny in it. Label it checking or kinetic energy. You could do a scrap piece of paper. It's nothing special. Put a box that says kinetic energy, and another little box could fit a penny in it, saying potential energy. Okay. So we're going to do this analogy here. Okay, potential energy is savings account, kinetic energy is checking account. Total money in the bank is the sum of your checking and your potential. Sorry, checking and your savings. Okay, work done by a non-conservative force. That's like withdrawing or depositing money into the bank. Okay, so what? That's a chemistry question. All right, so when we're doing these problems, there's two steps for setting it up. Number one, do you remember how we were talking about the truck going 60 miles an hour north and then 60 miles an hour south? Okay, and the whole point of that question was it's a process. Okay, so it's really important that we define what our initial and our final conditions are. So here we're going to say initial conditions when the kid's at the bottom of the hill, and the final is when they're at the highest point. Okay, that's the first thing we do. Second thing we do is we need to define what ground zero is. The lowest point we care about, where is height equal to 0? In this case, it's right here. Height is equal to 0 right there. Okay. Now, at the initial point, we're going to ask ourselves, do we have kinetic energy? How do we know? Well, kinetic energy, we're asking the question, is it moving? Okay. At the initial position, is the sled and the kid moving? So we're going at the initial, are we moving? Yes. So we have kinetic energy, so put some pennies into the kinetic energy square, into the checking square. How many? I don't know. What do we want to do? Like 5? It doesn't matter. Just give yourself something. Okay, so put some pennies into the kinetic energy category. All right. At the initial location, do we have any potential energy? Gravitational potential energy. Question we're asking ourselves is it above ground zero? Is it above ground zero initially? So the answer to this is no, we're at ground zero, so no potential energy there. Good with that? So relationship number 1 says this. My kinetic energy plus my potential energy equals my mechanical energy. My checking account plus my savings account equals the money in the bank. Okay, how much money do I have in the bank? Well, I gave myself 5 pennies, so I have 5 pennies. Does that make sense? That's relationship number 1. My checking plus my savings gives me the money in the bank. Okay, so that's my initial scenario. Okay, then I ask myself, is there any work done by non-conservative forces? Okay, so is there any work done by non-conservative forces? So in this scenario, what do we say? Oops, this sled slides up an iced embankment until it momentarily stops at the highest point. Ignore friction. Tell your neighbor yes or no for work done by non-conservative forces. Work done by non-conservative forces gives you thumbs up for yes, thumbs down for no. Any work done by non-conservative forces in this scenario? No work done by non-conservative forces. So what can we conclude about the mechanical energy? Is it conserved or not? Yes, it is conserved. Here's the second relationship. The initial mechanical energy plus the work done by your non-conservative force gives you your final mechanical energy. We said that there was 5 pennies in the bank. We didn't take any out or give any. So how many pennies are in the bank at the end? 5. We're still at 5 pennies. The total amount of pennies was conserved. The total amount of mechanical energy is conserved. It stayed the same. Good with that? And then relationship number 3 says, well, where is that money distributed? Like it's in the bank, but which account is it in? Okay, or in both. So at the end, do you have kinetic energy? At the highest point, how fast is it going? 0. So do we have kinetic energy at the end? No. Do we have potential energy at the end? Are we above ground zero at the final location? Yes. So how much money do I have in my savings account? All of it. 5 in this scenario. Because I've got none in checking. It's all in savings, all in potential energy. Good with that? Okay, so these bar charts are like energy accounting. Where's it going? Okay. So these help us answer these type of questions. How did the change in kinetic energy compare to the change in potential energy? How did the change in kinetic energy compare to the change in potential energy? So looking at these bar charts, the kinetic energy, was it gained or lost? It was lost. We went from something to nothing. Okay. What was the value of the change? -5 pennies. Okay. Did potential energy gain? Was it gained or lost? It was gained. How much did it gain by? 5 pennies. Okay. So tell your neighbor the correct answer. Correct answer is C. Good with that? Okay. Now, here's a factoid. If mechanical energy is conserved, then the change in kinetic will always equal the change in potential. One will be positive, one will be negative. One's gained, one's lost. But the change is the same. That's how you get it conserved. Good? Okay. What would happen if we added friction to this scenario? Okay. Would there be work done by a non-conservative force? Yes. Okay. So, how much work? I don't know. Something. Let's say it took 2 pennies away. Okay. Just made that up. Negative. Okay. So, what's my mechanical energy at the end? Start of the 5, I took away 2, I ended up with 3. So how much potential energy do I have in the bank? In my savings account? 3. What did that, how's that how's that represented in life? What was the consequence of that to the sledder? It does slow down, but it doesn't. It does stop, but potential energy has to do with what? How high it went. So with friction, it wouldn't go as high. Good with that? So with friction, answer this question. How did the change in kinetic energy compare to the change in potential energy? Tell your neighbor.
Can you go back to the previous slide, please? Kinetic energy cost. Oh, wait. Okay.
Correct answer is A. Whatever is, if mechanical energy is lost, whatever is lost is going to be more than what's gained, because you ended up with less than what you started. Okay. Good with that? Okay. All right. So let's throw some numbers at it. All right. You throw a rock at 25 meters a second at 30 degrees off of a 10-meter high cliff. How fast is it going when it hits the ground? Okay. So this is a projectile motion problem, but we're going to take it. We're going to evaluate this from another perspective with work and energy. Okay. So we're going to define, first step is define our initial and final locations. So initially and then finally. Second thing is we're going to define ground zero, the lowest point we care about. In this one, it's screaming obvious. It's going to be the ground. Okay. And then what we're going to do, step 3, is we're going to write this equation. Remember creating this on Friday? Your initial kinetic energy plus your initial potential energy is equal, plus the work done by non-contributive forces is equal to your final kinetic plus your final potential energy. Good with that? So hopefully you see some similarities here with what we just went through. Kinetic energy initially, do you have it? Initial kinetic energy. This is after it leaves your hand. Do you have kinetic energy? Thumbs up, thumbs down. Initial kinetic energy. Thumbs up, thumbs down. Yes. You do have kinetic energy. So, how much kinetic energy? I don't know. But you need to put some pennies in your checking account. Put some pennies in your kinetic energy. Let's say 25 meters a second. That kind of seems, I don't know. Throw in 3 in there. I don't know. Made that up. Okay. Do we have gravitational potential energy? Initially. Yes. Why? We're above ground zero. So we have potential energy. How many pennies should I throw in there? I don't know. It's on top of a cliff. I'm going to give myself like, I'll say 5. I don't know. Okay. So how much money do I have in the bank? I've got 8 pennies in the bank. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I got 8 pennies in the bank. Okay. In this process, going from my initial to my final, was there any work done by non-conservative forces? Thumbs up, thumbs down. After it leaves your hand, right before it hits the ground. Was there any work done by non-conservative forces? What do you say? Thumbs up, thumbs down. Yes, there was work done by non-conservative forces. No, there was not work done by non-conservative forces. As it goes through the air, what force is acting on it? Just gravity. Is gravity a conservative force? Yes. So there are no non-conservative forces doing work. Okay. So what do we conclude about mechanical energy? Was it conserved, lost, or gained? It was conserved. So I still have 8 pennies in the bank. Good with that? At the end, do we have kinetic energy? It's right before it's like if I dropped a bowling ball on your foot, does it hurt? Yes. Why? It's heavy and it is moving when it hits your foot. So, yes, I have kinetic energy. Do I have gravitational potential energy? At the end, we're going to say essentially zero. We're at ground zero. Okay? So, we have no potential energy, so no money in the savings account. So where's my money? So that 8 pennies needs to be distributed between checking and savings. We just decided that there's nothing in potential. So all of this needs to be, all 8 pennies is in my, 1, 2, 3, 4, 5, 6. Make that a really thick penny. Yeah. 8 pennies there. Good? So now we stick in for kinetic energy, we substitute 1/2 mass times speed squared initial plus mass times acceleration of gravity times initial height. Plus, I don't expect you to do this. We've discerned that's zero. It's equal to final kinetic energy, 1/2 mass times speed squared. Final plus, we've figured out that there is no gravitational potential energy. So plus zero. I don't expect you to write the plus zeros. I'm just trying to teach. Okay? Good with that? Now, do you see that there is mass for in every expression? Mathematically, what could I do to simplify that? I could cancel out. I could divide by mass. Okay? So, if mass is in every expression, then it cancels out. Okay, if mass is in every expression, then you can cancel it out. And so I get 1/2. I'm going to plug in numbers here. 1/2, 25 meters per second. Square that plus 9.8 meters per second squared times height of 10 is equal to 1/2 final speed squared. Okay, so 25 squared, bless you, times 0.5 is 312.5 plus 98 is equal to 1/2 mass times speed squared. This equals to 410.5, and this is equal to 28.65 meters per second. Okay. Mathematically, what do we not deal with? What is it that we did not, like we just ignored? Okay, we ignored mass. Oh, okay. So what does this mean in real life when the mass cancels out? Does that mean it's massless? No. What could it mean? Okay, maybe. So what this means is the mass of the rock doesn't matter. I could have a 0.25 kilogram rock. I could have a 25 kilogram rock. It doesn't matter. So long as I launch it at 25 meters a second at 30 degrees, it's going to hit the ground at that speed. Okay. What else do we not incorporate mathematically? What? Okay, yes, the pennies. That's true. The pennies are more conceptual. Did I give you a number that we didn't ever use? 30 degrees. Doesn't that like with projectile motion, we would totally do that, right? We would like find the components. But what does energy not have? Direction. So it doesn't matter the angle. It does not matter the angle. That's kind of nice. Hold on.
Is the 1/2 going to get used?
I did. I multiplied it. Oh, sorry. I forgot to. I did. So that. Sorry. Yep. That's 821. Final speed is 28.65. Bless you. Good catch. Okay. Good to that. Is 28.65, is that in the realm of possibilities? Started at 25 meters a second, ended up at 28 meters per second. Yeah, sure. Good with that? Okay. Any questions on this example before I go to another example problem? Okay, so this is how you bake a conservation of mechanical energy problem. These are the steps. Just walk you through it. Okay. This is how you draw your energy bar charts. Okay. All right. 500 kilogram roller coaster is going 1 meter a second at the top of a 20-meter tall hill. Plunges down and races back up a loop. How fast is it going at the top of a 15-meter high loop if friction is doing negative 3,000 joules of work? Okay. So our initial location is here. Final location's here. Where are we going to make ground zero? The lowest point I care about between my initial and my final is right here. I'm going to make this ground zero. But it goes below that. Yes, it does. But I don't care. Okay, all I care about is which is lower, the initial or the final. Whatever is lower, I make that ground zero. Okay, so initially, okay, initially, did I have kinetic energy? Thumbs up, thumbs down. Did I have kinetic energy initially? On 1 meter a second. Yes, I did. So how many pennies should I put in there? It's not very fast. 1 seems appropriate. Okay. Did I have gravitational potential energy initially? Yes, I was above ground zero. How many pennies should I throw in there? I don't know. What do you want to say? 4, 5, whatever. Okay, 4. Okay. So how much money do I have in the bank? I have 5 pennies. Okay. Was there any work done by non-conservative forces? Yes, there was. And was it positive or negative? Negative, so it's taking energy away. So I'm going to say we're going to take 2 away. I don't know. Okay. So our second relationship, if I started with 5 pennies, I took 2 pennies away. How many pennies do I have left? 3. Okay. At the end, do I have kinetic energy? I hope so. That would stink to stop at the top, like, okay. Do I have gravitational potential energy? If I made this ground zero, no, I don't. Okay. I'm at ground zero. So there's nothing here. So all my pennies are in my checking account. Good with that? Okay. So here I go. Got 1/2 mass times speed squared initial plus mass times acceleration of gravity times height initial plus the work done by non-conservative force is equal to 1/2 mass times speed squared final. Woo! Can I cancel out masses? I cannot. I don't have mass right there. Okay. So I have 1/2 times 500 kilograms times, 1 meter per second plus 500 kilograms times 9.8 times, what's my height above ground zero? It's 20 minus 15, so 5 meters. Okay. Minus 3,000 joules of work is equal to 1/2 500 kilograms times final speed squared. How many unknowns do I have? Just 1. I solve it, and I get 9.3 meters per second. Okay? Got a worksheet due tomorrow, which I'll post momentarily.